Are there any questions before we get started? Okay, let me continue with the review of linear algebra. As I said before, it's extremely important that you understand what linear algebra is. And there's just 2 more points that I'd like to go over, which is how we find the trace of a matrix. Okay, we have a matrix A, which is usually A11, A1n, and then AN1, ANn. And then the diagonal elements are given by this. The trace of the matrix A is just the sum of the diagonal elements. So it's a very simple operation. So if you have the trace of A, it's just equal to sum of the diagonal elements written in this manner. So you just sum these elements up, you make the 2 indices the same, and then sum them up as the trace of a matrix. But it has some interesting properties that you should know. Okay, it's that trace of A plus B is obviously equal to trace of A plus trace of B. Okay, this is quite obvious. And then if you have trace of a constant times A, is a constant trace of A. Okay? And the trace of a matrix A is the same as the trace of its transpose. And then trace does not depend on order. That is, if you multiply 2 matrices together, it is the same as the trace of its reverse order multiplication. That we can prove very easily. Trace of A dot B is equal to, first you do the inner multiplication, it will be Aij and then Bjk. But in order to find the trace, you have to set k equal to I, and then you have to sum. The outer summation is over n, the inner summation is also over n. Okay, so you can see that if you can revert this order, it doesn't matter because the summation remains the same. That if you were to reverse the order, reverse the summation, then it's just Bji, Aij. Okay, so trace does not depend on the order of the matrices, and that you can show this that trace of a similarity transform. So if you multiply a matrix A by a similarity transform by P and its P inverse, because trace does not depend on order, this order can be also extended to 3 matrices and so on. So we can actually reverse the order of some of this thing and write this as trace of A dot P. This matrix was followed by this matrix, and hence this is the same as the trace of the original matrix. So the trace of a similarity transform matrix is the trace of the original matrix. You can show that trace of a matrix A is also equal to sum of its eigenvalue. Okay. So those are some of the properties of traces that we would use in the course. And one of the things that you might notice is that if you have an outer product, say a vector B, outer product with a vector W, you can write it in matrix notation as such. This is equal to the matrix B times the matrix W in this manner. And that you can write this as being equal to, you can write this as being equal to BWT as being equal to VIWJ. Okay, VIWJ, the ij element of this matrix is VIWJ. So if you will take the trace of an outer product, okay, it will be equal to VIWI. And it becomes an inner product. Okay, you can change an outer product into inner product just by taking its trace. Okay, that is something that we might use. Again, and then I'd like to talk about the function of a matrix. I talked a little bit about that, but let me just elaborate that again. That if you have an exponential of a matrix, it has no meaning unless you expand this in terms of a polynomial. Okay, so we know that this has a polynomial expansion plus x squared over 2 factorial plus x cubed over 3 factorial plus. So function of a matrix is to be interpreted as a polynomial of a matrix. So if you have something, you should think of this as the polynomial of the matrix. Over 2 factorial plus a dot a dot a over 3 factorial and so on. Okay, then this has meaning that is a function of a matrix has no meaning unless it acts on a vector. Okay, and then you can substitute this in here and act on a vector, and you know how to do each of the operations. So function of a matrix has no meaning unless it acts on an operator vector, and when that acts on a vector, you expand it in terms of a polynomial of a matrix. Okay, so if x is an eigenvector, this actually greatly simplifies. Say if x is the v, and then it has this property that when a x on v, it just gives you its eigenvalue. Then you can easily show that a squared dot v is lambda square v. Okay, quite easily you can show that, and then you can show that a cubed dot v is lambda cubed v. So if you have EA operating on the eigenvector of A, and if you do each of this term, you will have 1 for the first term, lambda for the second term, lambda square for the third term, lambda cube for the fourth term, and so on, operating on V again, just using eigenvalue property. So this is e to the lambda dot t. So you can see that a matrix function operating on the eigenvector V is just the matrix replaced with eigenvector times the vector V. Okay? So if you have a general vector W, you can always expand this in terms of sums of eigenvalues of the system. Then if you have a matrix operator operating on the general vector W, you can take this inside the summation. Okay? And then you can replace this with just AI e to the lambda I vi I e to the 1 to n. So this is the general meaning of a matrix function operating on an arbitrary vector V. So, if you have an equation that you sometimes might see in electrical engineering, that you have dW V of t dt is equal to A dot W of t. You can actually formally integrate this equation and write this as e to the AT times W of 0.
Professor,
Yes?
can you turn on the lights?
Oh, sorry.
First one, yeah.
Okay, thank you. So, you can formally integrate this equation in this manner. Actually, you can go through the eigenvalue analysis. You can expand W in this manner and validate this solution. This solution is in fact the correct solution. Because when this operates on that, you will have to expand this in terms of its eigenvectors, and then you can show that this formula is a solution. So oftentimes, when you have a matrix operator, You can think of it as being replaced by its eigenvalues, but you have to go through this formal process to replace it by its eigenvalue. Okay, that is what I want to talk about in terms of the review of linear algebra. Do you have any questions so far? Okay, if not, then let's move on to talking about some quantum mechanics then. And let's talk about solving Schrodinger equations and what we can do from there. So, as we said before, if you have a classical particle, if you know its position q, or sometimes we call it x, okay, and if you know the velocity q dot, you can formally trace this particle and see how it goes through, say, phase space, say q dot q. Okay, you can denote a particle in phase space as a point. If the particle starts out t equal to 0, it has this velocity and this position. You can formally integrate this information and figure out where the particle should be in the next moment. Okay, delta t later. And then you can formally find out this kind of thing. So you can see that the equation of motion, as Ian has shown, is that the rate of change of momentum, p is the momentum, is equal to the force. And then rate of change of position, which is the velocity, is given by p over m. So this can be the equation of motion. And in order to solve this equation, you can formally write this, say, as a differential equation. So I could, for instance, write this equation as V as being consisting of two unknowns, P and Q. Okay, V can be something that contains P and Q, and then I can write this equation formally as this. The equation of motion can be written as a matrix equation such as this one over here. And these are the classical equations. But Schrodinger equation is quite different, and quantum mechanics is quite different. It says that in addition to endowing a particle with just its position and its velocity, we need to give a particle more things. Okay, it has to be given not just its position and velocity. We have to give the particle a wave function that it should be associated with. So, in order to describe the behavior of this particle, we have to introduce Schrodinger equation, which governs the behavior of the wave function. And from those wave functions, you can get classical quantities like positions and momentum and velocity and so on. Okay, so that's why we say that this equation that we discussed earlier was proposed by Schrodinger, and then this potential can be also a function of position. And the wave function has to satisfy this equation, and that can be a wave function, say, inside an atom, where V has a Coulomb potential that might look something like this. And this is R, say. And this kind of potential can potentially trap a particle wave function just like dielectric waveguides do, as you have learned in ECE 350. So if you set up a wave traveling around, you might get different modes being trapped. Maybe there's a mode that's looking like this with eigenvalue. This is eigenvalue of the problem. So this is eigenvalue of the problem. You might have one that has E0, and then you might have one that might have E1 that looks like this. And the wave function will look something like this. And then you might have one that where the wave function might look something like this. Okay, E2. So this equation has to be solved for all these different trap modes, as they have done in ECE 350 in solving for the trap modes of a dielectric waveguide. Okay? And this should be a plus then. This should be a plus over there. And then how do we explain what these wave functions are? So it baffles physicists and researchers as to what these wave functions were, but it was not until Born who came up with a probabilistic interpretation of the wave function. He says that this wave function should be associated with the probability of finding an electron in a certain position. So if you have a wave function psi of r, the probability of finding the electron in this volume V, say if you have a wave function, this is a 3D wave function. Okay, the wave function is a continuous function of space, and if you have a delta V in space, and the probability of finding an electron in that small volume is proportional to this quantity. So this wave function square should be thought of as a probability density function. Or PDF. Okay, so it should be thought of as a PDF. That was Born's contribution. And before that, people didn't really know how to interpret. Even Schrodinger himself thought that the wave function has to be something to do with the charge cloud. But that interpretation is not accepted now. It is that the electron should be everywhere. Okay, the electron can be found everywhere before you do the measurement. And if you do a measurement and find an electron over here, and the probability of you finding the electron there is proportional to this quantity. So it's something that you have to learn how to accept. Okay, electron is everywhere before you do the measurement, before you find it, and after you found it, this is the probability of finding it at this particular location R. Okay? So because these are probability density functions, they have the property that if you square it and then integrate over the total volume, and this should be equal to 1. Okay? And this is even true for time-dependent Schrodinger equation. We say that E is found to be h bar omega, and minus I omega is equal to partial t. Okay, because we assume this kind of time dependence in this course, as most physics courses do. So h bar omega could be written as I h bar omega. H bar omega can be written as I h bar partial t. Okay. H bar omega can be written as I h bar partial t, and you can also derive a time-dependent Schrodinger equation psi RT plus B of R psi of RT equal to minus h bar partial t of psi of RT, where we've just replaced this quantity here with h bar omega, and replacing that we get that equation over there. Okay? And this is also true for time-dependent wave functions, that at a given time, this thing has to integrate to 1. Because this has a probabilistic interpretation. Okay? So, we can write the Schrodinger equation in a very suggestive fashion. If you think of this as an operator, you can think of this as an operator that some sort of an operator operating on psi RT is equal to the same as h squared over 2m Laplacian plus B of R operating on psi RT. So we have learned how to manipulate matrix operators, But differential operators and these operators are actually the same as matrix operators. Okay. For instance, if you need to take the derivative of a function like partial x or psi of x, you can think of that as being equal to psi of x plus delta x minus psi of x over delta x. And if I were to discretize space and call space to be 1, 2, 3, and so on, this is I plus 1. And if I label my I position to be x, the I plus 1 position to be delta x, I can write this as being equal to psi of I plus 1 is valued at I plus 1 minus psi of I divided by delta x. Okay. So a differential operator can be thought of as some kind of a matrix operator where you have the unknowns stack up in a column vector psi I plus 1, and so on. You can stack up these unknowns into a column vector, and then your differential operator is nothing but with the minus sign over here. If we put a minus sign and then put a 1 over here, and let this be 0 otherwise, then if you let this matrix operator operate on that, it will approximate this value, and you have to divide by delta x. So a differential operator is like a matrix operator of some sort. Okay. And then you can also think of a scalar operator, like B, B of x, psi of x. If I were to write this in the discretized form, will be B of xi times psi of xi. Okay, evolves to this, and then this can be thought of B of I times psi of I. Okay, this can be thought of as just a diagonal matrix. Psi 1, psi 2, psi I, psi n. And then you can just put B1, B2, B3, B4, Bn here, and then put 0 anywhere else. If you multiply these two out together, you essentially get this thing over here. So even this can be thought of as a matrix operator of a diagonal kind. This is a matrix operator of a quasi-diagonal kind. So we can think of this as something like a matrix operator. But in the continuum space, we call this Hilbert space operator. Hilbert space is a continuum representation of the discrete space that you learn in linear algebra. Okay, when we extend this to the continuum space, we call this Hamiltonian operator. Okay, so this can be a Hamiltonian operator, and we usually denote an operator with H hat. And if I were to write down the equation of motion for this thing in terms of an operator notation, I can think of it as H of psi being equal to I H bar d psi dt. Okay? So this is very analogous to the matrix times the vector is equal to d dt of the vector. Very analogous to this equation. And we formally integrate this equation, and we can formally integrate it as psi as a function of time is equal to e to the minus I h hat over h bar t times psi of t equal to 0. Just like we can formally integrate this to the b is to the e to the at times b of 0. Okay, you can prove by eigenvector expansion. So we can formally integrate this, and this is perhaps the first time you see something like this. It's actually not very strange to see this in the matrix form, but to see this in the Hilbert space form is a little bit strange to you, because then everything is actually expressed as a continuum in Hilbert space. There's no indexes or indexing like what you see in the discrete space. So, in order to have this meaning, to give this meaning, you have to find the eigen functions of H. Okay, eigenfunctions of H are defined to be functions such that when it's being operated by the Hamiltonian operator, it's just an eigenvalue times size of n. So this is analogous to A dot bi is equal to lambda I bi. So this is entirely analogous to this in linear algebra. And once you have that, then you can actually evaluate this equation for eigenfunctions very easily. If psi n is an eigenfunction, okay, you can actually evaluate this if this is an eigenfunction, and as we said before, if a function of a matrix operator operates on an eigenvector, you just replace that matrix with its eigenvalue. So similarly here, you can prove that this is equal to just IE n over h bar t size of n t is equal to 0. So this is something that you can do in Hilbert space. Are there any questions so far that we can do operations like that? If you're comfortable with that, that's very good. We can proceed and do more of this kind of thing. So hence it's very important that you know matrix algebra or linear algebra. Learn how to think in terms of matrix equations and extend this matrix concepts to operator concepts. So this H is entirely analogous to your matrix operator A when we do things like that. Okay. And since we always say that E n is h bar omega n, so we can say that En over h bar is equal to omega n. So that time dependence there, we can say that psi n of t is equal to, I guess, e to the minus I omega n t psi n of 0. T is equal to 0. Okay? So we have this kind of very simple time dependence. And then we can use this kind of concept to solve a general initial value problem. That is that if we have a wave function known in the initial time, we can always expand this initial wave function at t is equal to 0 in terms of its eigenfunction. Sum over n. N usually can be infinitely large in Hilbert space. But for a practical space, we usually truncate this space into something smaller. So n can go from 1 to infinity in the Hilbert space. There's the only difference between Hilbert space and linear algebra in the sense that in Hilbert space, you often have to sum this over infinite dimension. So if you know the eigenfunction of the system at t is equal to 0, we can use this property to find this function at a later time just by operating on that, and then you can see that psi of r t is just equal to I h hat over h bar t psi of r t is equal to 0. And then you substitute the second equation in there, then you just exchange the summation, have this operating on this, and as this equation is true, then you can say that this is I omega n t psi of n r t is equal to 0. So we can use this kind of eigenfunction concept to solve a general Schrodinger equation. Okay. So are there any questions so far regarding on how we solve Schrodinger equation in general? Okay. And as I said before, this is a very good example of a Schrodinger equation. And this matrix, this actually is a scalar function. You can think of a scalar function as an operator also, but the diagonal operator. So we often would write the Hamiltonian as being equal to the momentum part. This actually comes from the momentum of the particle. This comes from the potential energy of the particle. You can write the Hamiltonian as being just the momentum squared over 2m plus the potential operator hat. And you think of this E hat as being a generalization of this diagonal operator. And as we have learned before, P is equal to h bar k. So in general, a vector P is I h bar del. Okay. So in general, an operator P hat is given by I h bar hat, and then if you have P hat dot P hat, it will be equal to minus h. Sorry, it should be a no square here, right? Square here, and then you will have del dot del. That is what you should get, and hence this is equal to h bar squared del squared. So if you write this out explicitly, this is the same as h bar squared over 2m del squared plus v hat. Where v hat is actually a scalar operator, but we can think of it as a diagonal operator in this kind of notation over here. So we can write the Hamiltonian in a general sense in this manner. Okay. So if there's no potential to trap the particle, if the particle is just moving in free space, we have a rather simple equation to solve. Say, if we just have a problem in one dimension, this equation reduces to something that looks like that. Psi n q is equal to En psi of q psi of n q. This is 1D. Okay, in the 1D Schrodinger equation, we just have that, and no potential to trap the particle. So this particle is free to roam. It can go anywhere it wants to. Okay, and then you can see that from your ECE 350, you learn that the solution to this equation must be something of this form. Okay, e to the plus or minus I k cubed. Or maybe you even have an unknown constant up here. Okay? So this is a general solution to the second order differential equation. If you plug that into the above, you can see that the first term becomes IH squared. D squared, the Q squared will just give you minus K squared over 2m, and then you have psi n q must be equal to En psi n q. And then you can see that En, which represents the energy of the particle, is h squared k squared over 2m. This is just the kinetic energy part. Because this particle is free to roam in the free space, the energy of the particle is just h squared k squared divided by 2m. So physically, you'll find that the larger k is, the higher the kinetic energy. So if the particle has very small k, which means that the wavelength is long, k is equal to 2 pi over lambda. Okay, if k is small, you are dealing with long wavelength wave function, but when k is large, you're dealing with small wavelength. This is k large. k small. And you say that this particle has less momentum than this particle. This particle with a highly oscillatory function has a higher momentum compared to the other particle. Okay? And then it might be interesting now to put this particle in a box and solve for Schrodinger equation and see what happens to this particle. So we can put this particle inside a potential well, but this potential well that we can design can be very simple. So let's think about solving this equation now. I change my notation to x, okay, from Q from this point onward, because x is often used in other courses as well. And let's think about solving this problem now, where Bx can be something that looks like this. We might have a value of maybe 0 here and maybe some other value of B1 over there, for instance. I'd like to mention again that this E is actually not absolute in the sense that if you have Schrodinger equation, you can always add a constant to that equation